Hi, my name is Jiang Yu. I am a PhD candidate in Harbin Institute of Technology in China, and will now present our paper Range-nullspace video frame interpolation with focalized motion estimation. This work is done during my internship at Tetras AI with multiple collaborators coming from Tetras AI and Shanghai Jiaotong University. Continuous time video frame interpolation aims at upsampling the temporal resolution of low frame rate videos steplessly by synthesizing the missing frames at arbitrary time steps. It is a fundamental technology for various downstream video applications such as video streaming, image stabilization, and video compression. A key challenge of this task is to find a continuous mapping from arbitrary time step to the latent scene motion to correctly render the target frame based on the low frame rate video. Typically, it was realized via two stages: motion trajectory fitting and frame synthesis. In the former, a parametric trajectory model is fitted from the optical flows extracted from input frames, which can be resampled at any time step to get intermediate motion. For representing such a motion model, the Taylor polynomial is often adopted with different orders. However, fitting trajectory models are prone to optical flow errors, which are inevitable due to occlusion. Besides motion fitting, the frame synthesis step faces the challenges of correctly inferring scene geometry. Particularly, the intermediate flows resampled from the continuous motion model only depict partial correspondences between the intermediate frame with input frames, while existing methods predict complete rendering rays in a data-driven manner to facilitate full rendering. Though powerful architectures and rendering mechanisms were proposed, it requires the network to fully encode the scene geometry to predict correct rays, which may raise the difficulty of architecture design and the burden of learning. To overcome these issues, we propose a novel framework with improved motion fitting and frame synthesis components. The first is focalized motion fitting, which extracts a set of optical flow candidates from the input video and assigns learned confidence weights to them. Confidence-aware, differentiable trajectory fitting is then followed, focalizing only the confident flows and producing improved parametric motion models. Such models, when resampled at the target time step, can produce accurate flows even at the occlusion boundary. For the latter, we follow the fact that intermediate frame synthesis is an ill-posed task and propose a deep solver based on the range-nullspace theory. Our solver decomposes the latent intermediate frame into several orthogonal image components and adopts different networks to learn each of them. Such physics-guided design encourages learning decoupled subtasks for each network, relieving the burden of encoding scene geometry. We summarize the contributions of this paper as follows. 1. A novel lightweight VFI framework is proposed, which refreshes the records of 7 out of 10 public VFI benchmarks. 2. The idea of focalized trajectory fitting, which improves parametric motion estimation in VFI and generates better resampling quality of intermediate flows. And 3. A new perspective that treats intermediate frame synthesis as an ill-posed problem, solved with a deep range null-space solver that decouples frame synthesis into several orthogonal tasks. Following the routine of previous works, our framework takes for adjacent input video frames I-1, I0, I1, I2 and generates intermediate frame IT for any given time t. Our pipeline starts by extracting appearance features for each input frame with a contextual network. In the meantime, optical flows starting from I0 or I1 to other neighbors are computed. The focalized motion estimation, FME, consumes optical flows and contextual features. It consists of 3 steps: flow confidence estimation, focalized trajectory fitting, motion resampling and refinement, and outputs motion specifications at a given time t. Bidirectional motions are inferred, regarding both time 0 and 1. Here, Fi to t and Mi to t are the resampled flows and occlusion relation masks. Finally, we feed these motion specifications at time t and contextual features of input frames into the range-nullspace synthesis, RNS, module. Given contextual features and candidate flows, the confidence estimation step dynamically weights optical flow candidates. The following warping residual is computed. Where phi-b represents the bilinear warping function that projects features Ci-b to time 0 with backward warping. Intuitively, the residuals are conveys rich information of appearance warping errors induced by flows. We map such residuals to confidence weights via a network W. Higher value of Wi indicates higher confidence of the flow values in F0 to I, which deserves more focus for fitting parametric motion trajectory models. In focalized trajectory fitting, We suppose that, in a short time interval around each pixel of I0, the motion trajectory is approximated with second-order Taylor polynomial, where a and b are model coefficients to fit, and tau is the temporal distance with respect to time 0. Solving a and b can be formulated with the weighted least squares. The optimal solution of this weighted least squares has the analytical form. All the calculations are fast to compute, including the 2 times 2 matrix inverse, which is closed form. This renders the solver an efficient layer when integrated into the whole architecture. In motion resampling and refinement. After model fitting, we can resample the intermediate flows f0 to t. Similar with previous works, we also learn to refine the resampled flows to get benefits from end-to-end training, and infer the visibility masks indicating occlusion relations at time t. This is achieved with a refinement network M. The refined intermediate flows and a soft mask indicating the occlusion order of pixels are to be used in RNS. The REST pipeline aims to synthesize the target frame at time t. Arguably, rendering cannot be fully performed with the resampled flows, which only depict partial correspondences from I0 or I1 to IT, and do not account for occluded pixels in I0 and I1. Instead of predicting full correspondences, we treat frame synthesis as an inverse problem and solve it with a theory developed for it. Our starting point is that given the unknown IT and forward flows f0 to t and f1 to t, we can relate these terms with the observations I0 and I1 as this. In this case, flow-based warping can be reorganized as matrix multiplication with h0 to t, h1 to t. The additive residuals upsilon represent image components that cannot be modeled by warping. Taking it as the latent to restore and iy as the measurements, we can treat as an inverse problem with linear forward operator ht. Solving general linear inverse problems is not trivial, especially when the distributions of the residuals upsilon t and the latent it are complex. In this paper, we instead embrace a non-iterative and fast alternative, based on the deep range nullspace solvers. Range nullspace theory states that if a forward operator H has right inverse, it is possible to define two orthogonal projections, range space projection R, and nullspace projection N. Regarding our problem, unfortunately, the forward operator HT has no right inverse. However, it has the following equivalent form. The appealing property of nullspace projection can be used to construct the following solver, where G dot is arbitrary vector-to-vector function. Different G dot lead to different reconstructions, revealing the ill-posedness of inverse problems. To get results that fall onto natural images, we implement G dot with a neural network trained to minimize the empirical errors on a dataset. Solving this equation is left to know the residuals upsilon. Though following complex, structured distributions, upsilon is mostly sparse and universally bounded, which can be approximated well with neural networks. Inspired by previous works, we use another network R dot to directly approximate HT inverse multiplied by the upsilon, which is also bounded. After yielding the result IT, we find a projection of the result into the constraint set. The overall working flow of steps is referred to this figure. The network R dot and G dot have many design choices, not limited to the following one we use. Note R dot and G dot form cascade structure, where the estimation result of R dot is the input of G dot. We also pass through intermediate features F in this cascade as unobstructed information flow. Multiplications with H0 to T or H1 to T can be done via backward warping, while with their inverse we use softmax splatting. We evaluate extensively on 10 benchmarks: GoPro, Adobe 240, X4K 1000 fps, Vimeo 90K, UCF 101, Davis and the easy, medium, hard and extreme subsets from SNU Film. Among them, GoPro, X4K 1000 fps and Adobe 240 are used to evaluate 8 times interpolation, while others are 2 times. Evaluated with extensive experiments, this method sets new records on 7 of 10 public benchmarks, outperforms state-of-the-art methods. Here are some visual results. That's all. Thank you.